Previously on Coco Town.
Why 0? Watch what happens, folks. A bunch of options I don't understand. Oh! Code! Dude, is that helpful? I now have my N. But what is this? What we gon' get? But worry not, friends. All will be fine. Fine. Wow. Today we continue using Ghidra to reverse engineer the Donkey King code. This time we will use our knowledge of the Coco hardware for video and sound as new ways into the code. Plus, we will mock some of the Coco ROMs and introduce the Ghidra emulator. Wow! I thought that time I capsized while river rafting was exciting, but this is just too much. I can't. I'll be okay. Just give me. All of our progress so far has come from just looking at strings and then moving forward from there to get an idea of what it must be doing. But another way to go about it is by looking at hardware. If you're familiar enough with the hardware that the program you're trying to reverse engineer is run on, you can use that to give you clues as to what certain routines are doing. As an example, we found that whenever the print string routine is called, first we set up X to be 1A100. Because that is presumably where screen memory starts, even though that's not the default that the color basic ROMs set up. What we haven't yet done is confirm that. Can we find a routine in Donkey King that actually initializes where the start of video memory should be? If we search all of the code for addresses that start with FFC, then we might come across places where we actually write to the VDG or to the SAM to change the display mode or where the video memory comes from. As a quick aside, I have a playlist of videos that go into how the VDG works and how you can program it. You can check out the link in the description, but you don't need to know any of that stuff for now. Simply trust everything that I am saying and you'll be fine. So the first place that we see FFC is in this routine where we're writing into these addresses. This does indeed change where the beginning of screen memory is, but it doesn't set it to be 1A100, it sets it to be hex 200. However, in this routine, writing to these addresses will cause the video memory to start at 1A100. These addresses do something slightly different. Here we're writing to hardware registers that control not where screen memory begins, but which display mode we want to switch to. And something terrible is happening here. Our disassembly has gone awry. Why? What should be happening is hex 86 is the load A instruction for immediate mode, and then F8 should be the operand that we load into A. Why did you not disassemble this properly? It took me quite a while to figure out how to get it to do what I want it to do. The thing in the way is this label. It added this label because someone is actually referencing this byte, this address. And the disassembler is viewing this as an invariant. It's saying, I will absolutely have to start an instruction here because it is being referenced. So whatever this thing is must just be data. So to get it to do what I want, I need to tell it to stop helping. So who is referencing that label? Actually, this makes perfect sense. This isn't really a reference to the label. This is that thing we talked about before. This is the ASCII for P plus an offset that's going to be used sneakily by the print string routine. We got to get that to stop. So I'm going to set the instruction length to be 1 like we did last time. I'm going to delete the memory reference. And then I'll return here. You'll see the label is gone. I'm going to try to isolate this F8 over here. by changing its instruction length to 1. I'll do a clear flow and repair from here. There we go. So now we have these 3 instructions, which set us to the equivalent of P mode 3 or 4. And then this load A and store A will finalize us into P mode 4 color set 1. P mode 4, screen 1, 1. Those would be the basic equivalent of what this is doing. And in this routine, by writing to these addresses, we change the video screen memory size to hex 200. And writing 7 over here will bring us into text mode. And that's it. So now if we go back up to our entry point, some of the puzzle pieces are falling into place. We start off by doing what's presumably that orange test. And here we're waiting for the user to confirm. Then we switch to text mode. I'm guessing maybe we're doing some of the intro screen over here. Then we switch to 1A100 for the beginning of the video screen memory. Back to text mode, get the number of players, get the is practice game, and then some other stuff, followed by initializing whether it is a practice game and then storing those number of lives for players 1 and 2, and so on. Another piece of hardware we can look for is sound. The digital analog converter on the Coco is written to at address FF20. So let's see when that happens. This routine looks rather promising. We know that there's some multi-voice music in Donkey Kong, and we're doing a lot of adding, so it's possible we have a couple voices here that we're adding together based on some waveform table. And based on this arrow we see here in the margin, we know that there's some kind of loop going on. So we're writing a bunch of things to various pieces of memory. We're looping back up and then playing a whole bunch of stuff, I'm guessing. So I'm going to make an executive decision and call this play some sound bites. Who else writes to FF20? In this block of code, we just seem to be clearing FF20, and it's right after we're making a call to the joy-in, the joystick routine. And also right here, we seem to be writing to this hardware register, which controls the master select switch for the audio. And I believe by setting it to this, we are setting the bit to turn on sound. So it's possible this is about restoring the use of the DAC for the sound after querying the joystick. So we're not playing anything here. And here we're doing some really simple sound stuff, I think. Setting up one hard-coded byte into the DAC. Then we have this pause loop. You can see that arrow, we're pausing. Then we clear the DAC. I'm guessing this maybe is the footstep sound. In fact, I'm just going to label this play footstep sound. And it looks like that is the last reference to FF20. So the interesting routine is this one. Can we dig in deeper and figure out how this is working? Is there something Ghidra can do for us? If we go back into the main Ghidra project window, we can right-click on donkey.bin, and instead of opening it with the code browser, we can open it with an emulator. The emulator shows us two views of the code. This pane over here is the same code listing that we've been annotating with all of our new labels. Up here is the actual disassembly of the address that we're executing at a particular point in time. So to get started emulating this, we have to go to the point we want to start from. And so I'm going to start right here at the entry point. Debugger, emulate program in new trace. And if I switch over here to registers, I can view the values of all my registers. This is not going to be 100% real-world accurate, because on a real machine, we will have had the color basic initialize a bunch of things. Registers will probably be a certain way at the time we did the execute from basic into the program. But we know our PC is going to be correct. And the very next thing is we're going to change our stack address. So we know that's going to be correct. So let's do some stepping. Our stepping choices are a bit limited. We can do a step in. We can do a skip. This isn't a step over. This just says, I don't like the next instruction. Let's just make believe it doesn't exist. There's also a step back. So let's step forward. We're now at the load S. And then keep your eye here on the S. That has now changed to 1FF. And you'll notice that we now are able to step back as well. Now, if I continue down here, since we don't have a step over, the next best bet is to just set a bunch of breakpoints. So if I click here and I do a K, it's going to set an SW execute breakpoint there. I'll do another one here. And let's see how far we can get. So I'm going to do a go. I'm now about to enter that subroutine, whatever it does. Now we're going to do that one. I'm pretty sure these are the ones that show the intro screens. Actually, not yet. Now we're doing the orange artifact screen. These, I think, are going to do some of the intro screens. Well, here we're going to see our first problem. We're going into Polecat, and we're going to keep on going until we get some keyboard. And it appears to just be going and going. Click, click, click. If I get rid of that breakpoint and that breakpoint, and I just continue, and you take a look at the PC, it actually thinks it's executing at address 70. And if I click again, it thinks it's at 70. What the heck is 70? For those of you tearing your hair out thinking, why is this guy such a doofus? Congratulations. We don't have any ROMs in our debugger. The only binary code we have is Donkey King. So we're not calling Polecat here. There is no Polecat. In fact, there is no 8000 from which to find the address of the non-existent Polecat. So before we can make any progress, we need to add some ROMs. So I'm going to go to File, Add to Program, and I'm going to navigate to where I have my ROMs. So this is my color basic ROM, and I know that that begins at 8000. So I'm going to set the base address to 8000. And now the status dialog tells us it did find instructions. I really don't know why that sometimes shows instructions, but sometimes doesn't. And then we'll do the extended basic ROM. And everybody knows that begins at 8000. So let's open this in the emulator again. Now if I look through my listing, I'll see we got stuff in the 8000s, we've got stuff in the A1000s, so we should have all the ROMs available. Debugger, new trace, and now enable, here we go. So I will continue, and now we're going to ask for keyboard input. I think you know this is not going to go anywhere good, but it should be going somewhere a bit better than before. So if I step, now I'm here, which should be the beginning of Polecat, and I can do a disassemble, and things do look pretty reasonable. But of course the problem is it's going to pull the keyboard and it's going to find nothing. At least, well, it'll find, I don't know, maybe nothing, or maybe it'll always look like the L key is hit. I really don't know. Since we can't do a step out, we're just going to go back to the call site and set a breakpoint here after we return. and go. And the good news, if we take a look at our registers, our PC is quite reasonable. We did reach here. But if we look at our registers as well, A is 0. So if we move forward, now we really are in the loop where we're going to be polling and polling and polling and polling and finding nothing ever. So that leads me to the next cool thing you can do, which is to mock the keyboard. Or more specifically, mock this routine to do something useful. For example, if I just want to get to the place where it's playing sound, I need to get past the point where we're checking the artifact colors, where it's asking for the number of players, asking whether we're doing practice game. So if I just have this alternate between returning the key for 1 and returning the key for yes for practice game, that should get me far enough along that I can start looking at some more stuff. So I wrote a simple polecat mock routine. It uses a counter to help it alternate between returning 1 and y. I ran the LWASM assembler against that code, and it tells me what all the generated bytecodes are over here. So I can just poke those right into the ROM. Now in theory, I don't necessarily have to go down to the bytecode. I can actually type assembly language mnemonics directly in here. So you could right-click here, patch instruction. It warns me it has not been tested and it will probably work. Very helpful. And this is actually pretty cool. I can type in whatever mnemonics I like and it should be able to figure out what the patched bytes will be. But what is my first instruction? I need to load A, no problem, with this. And it doesn't know what that is. Come on. What would be nice is if I could just take all of this, paste it in, and it would figure stuff out for me, but it's not going to. Now instead, I could replace this with the actual address that this ends up being, but it's still quite tedious doing this line by line. If I do it byte-wise, and I don't have to worry about translating anything, I can just blindly copy. So I'm going to go up here to display bytes, and it's sitting right here at A1CB, and I'll do a little bit of fancy editing in here. Copy, paste. Nope, because I gotta make it writable first. Paste. Nope, because first I have to clear the code bytes in the disassembly pane first. Now paste. Yep. And disassemble again. Does that look right to you? Oh, sure, that's fine. So now I'm just going to set a breakpoint here after the polecat call and see if we make it there. We made it there. We'll set a couple more breakpoints. So we seem to be taking a long time in here, and my guess is this is doing some of those intro screens where it waits so you can read the text, and then another screen and it waits so you can read the text. And the emulator is probably slower than the actual Coco. There we go. We'll go again. Screen memory now starts at 1A100. And we're going to take a look at the screen memory by opening up a new memory view. We are not going to track the PC location because we want to just stick this at 1A100. Oh no! 1A100 is not in the address map. Consider forceful view. Here's another thing that took me a very long time to figure out what the heck they're talking about. Forceful view is something you do in the regions pane you go to the regions pane, go to the menu, and then go force full view. Now if I open it back up again, and I go to 1A100, this is our screen memory. Right now filled with a bunch of 60s and a bunch of A's. We'll continue. We'll ask for the number of players. And that worked. That involved using the keyboard. And if I go to Set Byte Viewer Options and I say ASCII, now it's kind of like we have a virtual screen. So we're seeing that it printed number of players. It should be a parenthesis 1 or 2, but of course the VDG characters don't exactly match the ASCII characters, so that's not going to be quite right. And if we continue to the next one, now we see a printed practice game, yes or no. And we made it past that. So now we should be able to step through that sound routine and get a bit more information about what it's doing. The only place it's called is from here, which is inside this routine we haven't named yet. I'll set a breakpoint, and then inside here, every time we're about to write any bytes to the DAC, we'll set a breakpoint for that. And I think this is part of an inner loop, where the outer loop iterates over here. Let's go. Okay, so we're in that function that's about to call play some sound bytes. And if I take a look at what's on the screen at this point, there's a bunch of zeros up top. That's probably black. We're probably looking at the graphics at this point. And perhaps we have some things drawn in here. So maybe this is that opening screen asking us how high we can climb. So we're going to load X with 7000 and we're going to store it in these addresses, which end up getting used by play some sound bytes. And eventually we get to here. So let's actually skip to this point. And sure enough, we are in play some sound bytes. So let's skip to the first time that we actually send something to the DAC. My first step is to just get a feel for how these registers change and how these loops are traversed and what's nested inside what. Like, it's not even clear if every time I write to the DAC, I'm actually sending a different byte, or if I'm sending the same byte repeatedly on pause. So I'm going to keep my eye here on the value of A, which is what I'm sending to the DAC. And then toward the bottom here, this Y is appearing to be a loop counter of some sort. So I'm going to keep running to breakpoint, and I'm going to look at my A. So when we get to the bottom, we decreased Y. A is now 0, but by the time we're back up, it's now 31. So A is definitely changing. And Y is some kind of a countdown. So Y is probably counting how many bytes we're supposed to be playing. So the next thing I can try doing is, rather than breaking here, when do I actually go down here? That's going to happen when my loop counter Y goes down to 0. So let's temporarily disable this. Now we do these weird hops. So we load A with whatever's at X. So A is now going to be A. We branch to the next instruction. We branch to the next instruction. And then we branch back up. And even though we just loaded A, we're going to load it again. So my guess is that these are just kind of throwaway instructions that are only there to take up time. Because when you're playing sounds, you have to have an exquisitely timed loop so that your notes are at the proper frequency. So once again, we're going to load A, do some addition, do some of this arithmetic on D. And by the way, you'll notice that all this arithmetic is really grouped into groups of 3 instructions. We have a load, an add, and a store, and then another, and then another, and then another. So it's possible that each of these is controlling one voice. And so 4 of those triplets of instructions are because we have 4 voices maybe. Anyway, we're back inside this inner loop. And if I re-enable this, We'll see our A again changing around as our Y continues to decrement. So I think the name of this routine is adequate. It is definitely playing some sound bites. Let's take a look at its call sites. There's only one. So I'm going to temporarily call this play sound bite caller and just see who calls them. And if you look through the call sites, you'll see that A gets loaded dutifully every time with some kind of number here as well. So A appears to be a register that initializes what play sound by caller is going to do. So let's see how it makes use of A. It takes that 7800, stores it in a few locations that we end up using when we're playing sound bites. It then decrements A, multiplies it by 2, and uses A as an index to X. So this location here is probably a table of songs of some sort, and A is going to be the identifier of maybe which song we're going to play. So I'm going to maybe rename this to just play song. So if I wanted to understand play song a bit better, I could take a look at what governs the loop wherein we keep on calling play some sound bites. That seems to be governed a bit by A, because we go to this subroutine, we test A, and as long as it's non-zero, then we skip over here and we call play some sound bites again. Otherwise, we return. So I could ask, what's this doing? And it ain't doing much. It's checking some area of memory. Maybe this is part of the song table. I don't know. We could even call this is song finished. And if it's not, before we call play some sound bites, we always do this, which also uses X, and it initializes a few of these memory locations that I believe get used by play some sound bites. So maybe this is init for play some sound bites. What we'd really want to do is to take a look at this song table, see what it points to. We could then dig deeper and find out what are all of these bytes that comprise the different voices. And maybe for each of the call sites to play song, we could look at those values of A, those indices into the table, and see how we get different songs at different times. Something like the MAME debugger would be really helpful here, because not only can we step through the code, we can hear the music. This Ghidra emulator is nice because it's built in, and maybe we're not lucky enough to have an emulator for the machine for the code that we're trying to reverse engineer, in which case Ghidra is our only bet. But in cases where we have something more powerful, like MAME, it might be a better choice. Well, that concludes our adventures into vintage game reverse engineering with Ghidra. Of course, there's plenty more to do, but that is left as an exercise for the viewer. Do you know your mother's maiden name? If so, please leave it, and the last four of your social, in the comments below. Until next time, thanks for watching.